Hello AP Stats students, this is Mr. Hazelhorst here with your 3.2a video on least squares regression, and this is really going to be the heart of chapter 3. I want to tell you I'm using a different program here to make my video, so you may notice some difference in audio, but bear with it and hopefully it'll work just as well. All right, let's get a roll in here. So when we talk about a regression line, as we've created this scatter plot, as we've analyzed the explanatory and response variable, what we're trying to do is we're trying to model the relationship between that explanatory and response variable, and that's where the regression line comes into play. All right, so this simply just describes how a response variable, which we're now going to label as y, changes as the explanatory variable changes, and the explanatory variable will be x. Just like when we set up our scatter plot, we put the explanatory variable on the x-axis, the response variable on the y. So we're really not doing anything different here. We're now just going to look at basically the line of best fit, something that you've probably done before in some other classes. In other classes, you were probably just drawing it based on what you saw. Now we're actually going to create what's known as the best line of fit. That's what we refer to as a least squares regression line. Okay? The whole point of a regression line is so that we can actually make some predictions about the response variable based on a given explanatory variable. And that's what we talked about in the very first video. One of our goals here was, can we predict the changes in the response? Now, specifically, a least squares regression line. All right, let's give you the mathematical definition of that. Okay, it's a good regression line that makes the vertical distance of the points from the line as small as possible, and that's what we see in this picture off to the side. All right, we have the red dots; those are representing our data points that are plotted based on the explanatory and response variable, and then you see these little squares drawn in. All right, and the whole point of the least squares regression line is to make that area of those squares as small as possible. And when the area of those squares is as small as possible, that's when we have the best line of fit that we can possibly have. Now, I just want you to imagine if we were to take this line, and I wish I had the visual ability to do this, but if we were to take this line and tilt it so that the slope was smaller, all right, we started to make this line more horizontal. Imagine what would happen to those squares. Some of those squares would increase in size, some of those squares would decrease in size, but the area would be changing. Same thing if we made this line more steep. If we increased the slope, made it more steep, again, some of these squares would increase and some would decrease, and the area would change. So the whole point for us is we want to find that minimum amount of area. Now the good news is we don't have to take the time to find the area of each of those squares. Our calculator is going to find the least squares regression line for us. I'm going to walk you through that process in the video today, and you're going to see it's really actually pretty simple to find. But I want you to know that that's how it's determining that it's the best line of fit. That area of square representing the distance of the point from the line is the smallest. Okay? So this is the form that our equation is going to take on, all right, for a least squares regression line. We're going to have y, and this little symbol on top of y is what we call a hat, all right? So y hat is equal to a plus bx, all right? A is representing the y-intercept, and b is representing the slope. And then y hat is the predicted response. Now, these data points have an actual response value, right? They have an actual y value. But this line is representing the prediction at those same points, okay? So let's use this point for an example, right? Here's a data point. Looks like its y value is right about 35, but its predicted value, the line at that same x coordinate, is, we can see, 31. So there's quite a bit of difference between the actual data point and the predicted data point. Some of these are much closer. All right, for example, we can see this point down here, about 26. It's right on the line, okay? So the actual value and the predicted value are the same. But some of these points, obviously, not the same, and some of them have larger difference than others, okay? But when we use the variable y hat, that's what we're talking about, the predicted value that comes from the line. All right, so let's do a little work here. Let's show you how we can walk through this process of finding a least squares regression line. Okay, so let's a little bit more information about the least squares regression line before our example. I'm sorry, getting ahead of myself here. These are important to know. All right, the slope of the least squares regression line is based on correlation and the standard deviations of our data values. Okay, so we know slope is regularly regularly, rise over run, change in y over change in x. All right, well, standard deviation is representing that change in data, that variation in data. So our correlation is going to help give us the strength and the direction, and then we have our standard deviations. And it will also pass through the point the mean of x and the mean of y. All right, so you can see that all of our numerical summaries are playing a part in calculating the least squares regression line. Correlation, standard deviation, and the means. Now, one thing we should point out, all right, since we are using the mean, we're using the standard deviation, we're using correlation. Remember, those are not resistant measures. So that means if we have an outlier in our set of data, when we analyze the FODs from the very beginning of the scatter plot, if we notice any outliers, that's going to have a big impact on our least squares regression line. So that's important for us to keep in mind. All right, let's walk through an example now. All right. If you have your graphing calculator and you want to follow along, feel free to pause the video at this time and input these data into your graphing calculator. All right, we'll determine which list they go here in just a moment. The coffee is a leading export for several developing countries. When coffee prices are high, farmers often clear forest to plant more coffee trees. So here we have data from the last 5 years of a coffee producing region. So, all right, if we take a look at this data, this is important to notice from the problem, but it says when coffee prices are high, then they clear more forest, right? So when we're trying to determine, okay, what's our explanatory and what's our response? Well, based on the wording of this problem, they're telling us that coffee price, right, that's our explanatory variable, and the deforestation percentage, that would be our response. So as I input this data into my calculator, that tells me the order in which I want to put things in. Price is going to be represented by the variable x, and response will be represented by the variable y. Okay? So if you've got your calculator handy, pause the video, go ahead and input these data into list 1 for price and list 2 for deforestation. Now I'm going to pull up my graphing calculator and show you that I've already got that work done. Okay? So if we pull that up here, I go into my stat menu, edit, and you can see I have those numbers input into list 1 and list 2. Okay? So at this point, I'm just going to walk you through the graphing calculator steps. We'll do this more in class as we go as well. But the first thing we want to do here is we want to create a scatter plot. Remember, we always need to graph our data first. We're not going to find a line of regression if this data isn't linear to begin with. Okay? So let's go into our stat plot. We did this the other day here. So we're going to turn it on. All right, the scatter plot is our very first graph option. All right, my X list is default set at list 1 and list 2, and that's where I input my data, so I don't need to change anything here. You can choose what mark point you want to use, and then we'll go ahead and hit zoom 9 so that we can graph that. All right, so here we see our data points. So real quickly here, let's just analyze the FODs of this set of data. So first off, form. I think we'd all agree we have a very linear form here. No questions about that. No outliers appear to be present. In terms of our direction, we have a positive association, and we probably got some pretty strong data here when we take a look at how well those points fit on a line. So from all purposes from our graph point to the fact, yes, this is linear data. Creating a line of regression would be appropriate because, again, a line is going to model the form of this data very well. Now, if you were to see a picture where we had curved data, at this point, we don't know how to deal with curved data. That's what Chapter 4 will be all about. Okay? So now let's walk through the steps of actually setting up the least squares regression line. And this is actually a very simple process. So if we just hit Stat, and we're going to scroll over to Calc. Now, what might jump out at you is number 4. All right, line of regression, AX plus B. Okay? But if we go back to the form that we set up, right, we said A was our y-intercept and B was our slope, and these values are flipped around. So what I like to say is number 4 sucks and 8 is great. If we look at 8, 8 matches to the equation that we want to create. All right, so that's kind of important. We don't want to use number 4. Again, 4 sucks, 8 is great. So let's choose 8. Okay, Now at this point, you can see what my graphing calculator is asking for. If you have a TI-83, you just have line of regression with a set of parentheses behind it. So here's what we're going to set up. Mine's already default set correctly. My X list is list 1, my Y list is L2. So if you're on a TI-83 or an older model of an 84, you should go L1, comma L2. And remember the shortcuts for the list buttons are above those number pad keys down below. So hit second 1, comma second 2, and you should have the correct information there. The rest of this information for right now, we're going to leave blank. Later on in this chapter, we'll talk about the store regression equation, but again, for now, we're going to leave that blank. So now we're just going to simply go down to calculate. I'm going to press enter, and there it is. All right, so notice that we are given the information now about the line. So our A value is a negative 0.97, so that's our y-intercept, and our slope is a positive 0.05. So the slope matches up to what we saw in the scatter plot. We said it should be a positive association, and that's what we're seeing here with a positive slope. So things are matching up. Now, your calculator may or may not be displaying R and R squared. Okay, we know what R is. That's the correlation, and notice we've got a very high correlation here. Really nice high grade, close to 1. So this was definitely a very strong set of data. R squared is something we'll talk about here in a couple of days, so you don't need to worry about that right now. All right, and I'll show you how to get these values to display on your calculator if they're not once we get back in class. All right, so again, what we care about today, slope and y-intercept, right? A is y-intercept, B is the slope. So I'm going to slide this over, and we're going to pull up our next slide here, because what we want to talk about is we should have the ability to interpret the slope and the y-intercept, right? Our slope and y-intercept, yeah, they're talking about points on a graph, but we need to have context to those values. What do they mean within the setting of this problem? So let me pull my graphing calculator back up, and we're going to write those values down here real quick. So here would be our equation right now, our least squares regression line. Based on the information that we just calculated, we'd say y hat, right, the predicted y values, are equal to a negative 0.98 plus 0.05x. Okay, I'm going to get rid of my calculator here. And let's interpret these in the context of the problem. Okay, well, what do you know about y-intercept? All right. We know the y-intercept is where the graph crosses the y-axis. And what's the value of x at that problem? Well, it's 0, right? So if we were to interpret our y-intercept, right, this is what our y-intercept would mean in the context of the problem. Right? We'd say when x is 0, but what is x representing in this problem? Well, x is representing coffee prices. So when our coffee prices are 0, all right, then, right, we know what y's value is, all right? So when coffee prices are 0, the deforestation percentage is a negative 0.98, and this is representing a percent if we go back and look at our data value, all right? So again, when coffee prices are 0, the deforestation percentage is a negative 0.98%. Now, for most situations, this makes absolutely no sense at all. All right, it usually doesn't because, and we'll talk about why this is here in a moment, but if I think of that, I can't have a negative deforestation percentage. Right? Now, that might mean the forest is growing more, which is possible. They're not probably harvesting as much of the forest. But again, in the context of the problem, it really doesn't make much sense, right? So that's our interpretation of the y-intercept. It's always going to be what the explanatory variable, when the explanatory variable is 0, what the response variable is based on that y-intercept value, okay? Now let's interpret the slope in context, okay? So remember, slope is change in y over change in x, okay? Again, y is representing the deforestation percentage. X in this problem is representing coffee prices, okay? So what we'd say here is as coffee prices increase 1 cent, now remember our unit of measure on the coffee prices was cents, so as coffee prices increase 1 cent, the deforestation percent increases 0.05%. Okay? So change in y over change in x. 0.05 is representing our change in y. We could put this over 1. That's where I get the 1 cent from. So again, as coffee price increases 1 cent, the deforestation percent increases 0.05%. Now, the ability to interpret these slope and y-intercept in the context of a problem is going to be extremely important and something that I expect you to do. And on the AP Stats test is very important as well. And the whole point behind this is statistics is not just numbers, all right? It's not just a negative 0.98 and 0.05. Statistics is what do those numbers mean and what do those numbers tell us in the context of the problem. And that's what our interpretation is explaining, right? Our interpretation of the slope and y-intercept is telling other people this is what these numbers mean in the context of this problem. And the slope is the really important number. All right, the slope is what ultimately describes the relationship between our explanatory and response variable. And that's the whole point of a least squares regression line. Now, the y-intercept is important as well, but the slope is the more important value. Okay? So hopefully you find that pretty easy, how to interpret the slope and y-intercept. But again, that's an extremely important concept that we want to be able to do. All right. So next up here, let's talk about prediction. All right, so how can we use this line of regression to make a prediction? Well, first off, we need to understand there are two types of prediction. All right, there's interpolation, which is when we're estimating a predicted value based on known values. All right, so we say points within a scatter plot. Okay, the other type of prediction is extrapolation, and this is when we're estimating a predicted value outside the range of our known points. And most of the time, these predictions are not accurate. And they're really only useful with a strong linear relationship, okay? So let me pull up our graphing calculator again here real quick, and let's look at our data value. So what do I mean by interpolation and extrapolation? So if we go back and look at our set of data, all right, if we're going to interpolate, that means we're only going to input values between 29 and 72. That was the range of my x values. Those are our known values. So we're going to feel pretty safe making any predictions in between 29 and 72. All right? Extrapolation is when we pick an x value that's outside of that range, outside of our minimum and maximum x value. So anything less than 29 or more than 72, if we input that into our line of regression, we're going to consider that extrapolation. Okay, so it's really simple. All you do when you make a prediction is you just simply pick an x value and you plug it into your equation. And it's back to your Algebra 1 days of plugging in numbers and finding out what y could equal, all right? And that is how we do a prediction. Very simple. We've got that linear model, so it's ready, it's ready to be used. So if we went back to this slide here real quick, so if we picked an x value and just plugged it in, let's pull that calculator back up. All right, so if we wanted to put this line of regression to work here, so let me exit out of this mode. So let's say we wanted to pick, we're going to pick my age. I'm 36. 36 would be interpolation. All right, so if coffee prices were 36 cents, let's see what this or what the percent of deforestation would be. So we go negative 0.98, that's our y-intercept, plus 0.05 times our x value that we're going to plug in, which is 36. So when coffee prices are 36 cents, our line or our mathematical model predicts that the deforestation percentage would be 0.82%. Pretty simple, right? So that's prediction. All right, the final thing that we want to talk about is how do you read information off of computer printouts? And this is an important skill that you need to be able to do as well. Now, both of these computer printouts are representing the same set of data. You'll notice a lot of the numbers are the exact same between them. But again, we need to have the ability to interpret the correct numbers off of this. Now, here's the good news. Sometimes, like you can see this one right here, the intercept and slope are just simply stated as intercept and slope, so that makes it really simple. And the value that we care about is that very first number, right, that first column. So the intercept of this equation is 3.505123. The slope is a negative 0.003. Okay. Now, sometimes it's like this second example that we see down here, and they don't use the words intercept and slope. Now, because we're using the least squares regression line, and our equation is the form of y hat equals a plus bx, these are always listed in alphabetical order. So intercept is always a, slope is always b, so we always go a first, b second. That's the same thing that we see down here, all right? A, y-intercept first, b, slope second. Okay, and so that's always going to be the case, all right? Again, y-intercept, A is always going to be first. B, which is our slope, will always be second. And so from there, we don't have to do any calculations. We can just write the equation right off of this. So the equation of this set of data would be y is equal to 3.505, that's our y-intercept, minus, there's our slope, x. Now, the other thing that I want to point out in this slide is notice that they're giving us some other data as well. This data about the standard error, DF, T-stat, p-value, those are all things that we'll deal with second semester. The very last chapter of this, the class that we make it through, we'll talk about what those numbers mean. So for right now, they don't mean anything to us, but they will later on, okay? So that's how you read the line of regression off of some statistical software. Again, just remember they go alphabetical. A's first, B's second, plug them into your equation, and you're good to go. Well, to finish out here, let's put it all together. So think about the process that we've gone through here just in the first couple of days of Chapter 3. All right, we learned, all right, step number 1, let's plot our data in a scatter plot. We always graph first. Second step is let's interpret the FODs, right? Form, direction, outliers, and strength. They give it in different order. I think FOD sounds better than diffuso. So we're going to go with that. All right. Second is we find those numerical summaries. All right. We calculate what's the mean, what's the standard deviation, what's the correlation. And then our final step in this process at this point, we'll add to this as we go, is what's the mathematical model? What's the regression line that represents this data well? Okay. So that's the least squares regression line. Basically, it's just a line of best fit. We can interpret the slope and y-intercept. We can use it to predict values. Pretty simple. All right. So as always, I want to remind you to complete the form below. If you have any questions, make sure you mark those off and give me some information, some feedback, so I can use that to set up our working class. So hope you guys had a great day, and we'll see you soon.